shape this morning. Just making a lot of stupid errors. Having said that, probably won't make any. That'll be the day. Okay. So we want to look at non-homogeneous second order equations, higher order equations. It doesn't have to be second order. So the higher order linear equation, usually it's going to be with constant coefficients when we apply this method, but not always. Okay, so example. I'm going to stick to simple examples because non-simple examples are still simple. Let's say we have y prime plus 6y y plus 6 equals e to the x plus x squared plus 2. And this is y double prime, this is y prime, and this is y. So see what I'm talking about? I'm not totally with it. Okay, so we got this equation. Now we can easily solve this. Okay, we get the solution set consisting of e to the negative 2x, e to the negative 3x. And you pretty much do that one in your head, but if you got to write it out, that's okay. Okay, so we have this solution set. Now, this is the homogeneous equation. So this is a homogeneous equation. If we plug any linear combination of these in to this equation, the result is going to be 0. And I'm just going to say what's going to happen. If we can find any solution to this equation, any function at all, y function, that solves this equation, when we add it to a linear combination of these, the linear combination is still going to give us 0. So we're still going to have a solution to this equation. So method's going to be fine. Any solution to the non-homogeneous equation and add to the general solution the homogeneous equation, and that's going to be a general solution to this equation. So any solution to this equation differs from any other by only some combination of these vectors. Now, coincidentally, in linear algebra, we're doing the whole idea that you take the null space of a homogeneous system and you add a specific solution to the non-homogeneous equation and you get the general solution. That's what I keep botching, but getting my numbers wrong. Okay, hopefully I'll get the numbers right here. Okay, so find a solution to the non-homogeneous equation, add to the general solution of the homogeneous equation. So to find a solution to the homogeneous equation, okay, let's just look at the e to the x. To get e to the x, from the left-hand side, we notice that if y equals e to the x, every one of these terms is just a multiple of e to the x. So let's find I forget what letters your text uses, but let y equal a e to the x, some constant multiple of e to the x. Well, I'm being easy on us. I don't have a coefficient on the x, so that all these derivatives are just e to the x. So that y double prime, if y equals a e to the x, y double prime is a e to the x. And y prime is a e to the x. And y is a e to the x. And there we have an equation that we can solve for a. And very easy to solve for a. And we'll go ahead and do it. This comes up to 12a e to the x. But of course, we don't need the e to the x there. We can divide it out. It's never zero. So we're not dividing by zero. We just divide out the e to the x. So we get a equals 1/12. So y is going to be 1/12 e to the x. So if 1/12 e to the x is part of our solution up here, it will give us e to the x over here. And if it was e to the anything but -2x or -3x, we'll deal with that. We don't want, well, it complicates things a little bit when what we have over here is one of our solutions of homogeneous equation. If the coefficient of x here was anything but -2 or -3, it would all work out. It's just that we'd have to take the square of the coefficient here and the coefficient here, and I think you understand that. So y equals 12 e to the x is part of the solution, and I guess I better write it out explicitly, of the non-homogeneous equation. And if you can read that on the recording, you won't be able to because of watermark, so let me just hold that up there. Okay, the conclusion is that this has to be part of the solution of your non-homogeneous equation. Now, more specifically, it has to be a term in the solution of the non-homogeneous equation. If your y function has 1/12 e to the x as a term in its solution, then this is going to give you an e to the x. And it'll still give you an e to the x if you add any solution to the non-homogeneous equation, to the homogeneous equation, because solution to the homogeneous equation is just going to give you 0. Okay. Now we want to do the same thing with the x squared and the 2. It's not as obvious what we might do for a trial solution. This is, okay, we let this equal a e to the x. We call this a trial solution. Okay, so this trial solution then pans out for us. It gives us a contribution, a term in the general solution of this equation. But of course now, a e to the x is not going to give us an x squared plus 2, is it? Okay, so now we need some function that has a property that when we add these multiples of the function first derivative and second derivative, gives us x squared plus 2. Well, let's go ahead and do that. Generally, if we have a polynomial here, which this is, we're going to let our trial solution, okay, this is a quadratic polynomial. We're going to let our trial solution be a polynomial of the same degree. So we try the general quadratic polynomial, and I'm going to use y equals ax squared plus bx plus c. Well, if we do that, then y double prime plus 5y prime plus 6y equals what? Well, y double prime is, take two derivatives, the x term and the constant term just go away, and we end up with 2ax squared. The first derivative is going to give us, and it's not 2ax squared, it's 2a. See what I mean? Something's not connecting. But anyhow, we get 2a from the second derivative. First derivative is going to give us 2ax plus b. And then six y is just going to be 6 times this, it's going to be 6 times this. Then we can find a, b, and c such that this expression equals x squared plus 2. Okay, well, that's straightforward. First of all, let's just kind of collect terms here to get the x squared, x, and constant numbers. So we have 6 ax squared. That's the only x squared term we get out of this. And then we have 10a plus 6b times x, and 10a from this, 6b from this, no other x terms. And then all the other terms are constant. and we're going to have a 2a and a 5b and a 6c. And we want that to equal x squared plus 2. So 6ax squared has to equal x squared. (10a plus 6b times x has to equal 0 because there's no x over here. So I'll say that that times x has to equal 0x, and two a plus 5b plus 6c has to equal 2. Well, that's pretty easy to solve because this thing is already gives us a set of linear equations that we can just solve by substitution, back substitution. In other words, or forward substitution. We'll do it in order. So this tells us that 6a has to equal 1 from this equation. (10a plus 6b has to equal 0. And 2a plus 5b plus 6c has to equal 2. Well, this tells us that a has to be 1/6. Then we got 10/6 plus 6b equals 0. So b has to equal what? Well, it has to equal negative 10/6 divided by 6, which is negative 10 over 36. And that's negative 5 over 18, if I've done that correctly. And what are the chances? Okay, extraordinarily straightforward. And then, wish me luck on this one. 2a is going to be, well, okay, we're going to get 1/3, then 5b is 25/18 plus 6c has to equal 2. You got a common denominator of 18. You're going to have to keep this in my head. And again, just take a shot and see if I get it right. If we multiply everything by 18, we get 6 here, minus 25 here, that's negative 19. Add that, add 19 to 2, we get 21, which means that 108c is 21. So C is 21 over 108, which reduces to 7 over 36. That might or might not be right, because I did a lot of it in my head. I think there's a fair chance that I got it right, but there's a huge chance that I didn't. So that I'm out of space, or maybe I'm out in space. This is linear algebra that I need to do something with, so I don't want to get rid of it. But it's talking about solution of a system is a solution of in the null space, or a solution of the homogeneous equation plus a particular solution, any solution to the equation. And we talk about the geometry of that and so forth. This is exactly analogous. So there's coincidentally, we're hitting the same idea. So now we're going to say YP, particular solution. Okay, now I haven't used that terminology, but a particular solution is any old solution of this equation that gives us this result. Any function y, which when plugged in here gives us these terms. And solution to the homogeneous equation, well, there it is. So we add any solution to the homogeneous equation to a solution to a particular equation, and we get the general solution to the equation. Again, totally analogous to what we have with null space and particular solutions in linear algebra. Okay, so anyhow, YP would then equal, in a question mark here, have to plug it in to the function and see if it really works. I'm going to say e to the x plus x squared over 6, because our solution here was, or our proposed solution was ax squared, and a is 1/6. We're going to have a 1/6 x squared. And then a bx will be as -5/18. And then plus c, which is, if I did it right, (7/36). And our general solution is going to be y equals C1 e to the -2x, which we get by just solving the homogeneous equation. Very straightforward. Plus C2 e to the -3x. This is our general linear combination of the functions in our solution space. Plus, I don't have room to write it out, but we would ordinarily then write out e to the x plus x squared over 6 minus 5/18x plus 7/36. Now you plug this into the equation, and it should give you a solution. Now it's going to be instructive to do that, so I'm going to figure out what to do with boards here, and I'm actually going to plug that in. So let me write it out here. Our equation was this. Our solution, question mark, is y equals C1 e to the -2x plus C2 e to the -3x plus x squared over 6 minus 5/18, was it? And 7/36. Let's check. -5/18 and 7/36. Yeah. Okay. Well, let's plug it in. Y prime would be -2 C1 e to the x minus 3 C2 e to the -3x, and it's e to the -2x, not e to the x. Okay, so these derivatives are straightforward. And then we're going to get x over 3 minus 5/18. And if you see me do something wrong, scream or something. And we get y double prime then equals derivative of this, which is going to be 4c1e to the negative 2x plus 9c2e to the negative 3x plus 1/3. Well, now we go ahead and assemble. You plug this expression in for y, plug this expression in for y prime, plug this expression in for y double prime. So we get going to be kind of long when we write it out, but it's going to be 4c1e to the negative 2x plus 9c2e to the negative 3x. And then it's going to be plus 1/3. And then it's going to be plus 5 times this quantity. And I'm going to go ahead and multiply through by 5. Limited board space, we don't have to get too messy, but 5y prime. Okay, so, well, here's your y double prime. And I'll kind of color code these things. Okay, so y double prime will be this. And then 5y prime. Being careful, we're going to get a negative 10 c1e to the negative 2x minus 15 c2e to the negative 2x. And that's going to be plus 5/3 x minus 25 over 18. I'm going to be shocked if this actually comes out correct. Let's see. So here's my 5y prime. So I'll just kind of circle this and this. There's our 5y prime. And that's going to be plus 6y. And we'll make that blue. So it's going to be 6c1e to the negative 2x plus 6c2e to the negative 3x. And that should, and right at this point, let's stop for a minute and see, okay, that ends everything that we get from the solution of the homogeneous equation. The characteristic solution is the term we use for that. Okay, so we've got 4c1 on the e to the negative 2x and negative 10c1, which is negative 6c1, e to the negative 2x, and a 6c1, so that's going to go away. Okay, because none of this other stuff, none of the solution to the I haven't made a mistake except that I didn't write down the 1/6 e to the x. I'll insert that in a minute. Okay, none of this stuff has any influence on what happens to this stuff because the terms all act independently. Okay, so we see that the c1e to the negative 2x gave us this, this, and this that added up to 0. And then c2e to the negative 3x would better add up to 0. Let's see, we got 9 of them. We got negative 15, which is negative 6, and plus 6. That's all goes away. So the e to the negative 2x's all go away. Now I've got to do something with this 1/6 e to the x. well, I'm going to have an e to the x over 6 here. And then I'm going to have a 5 e to the x over 6. Yeah, something's probably wrong with my 1/6 there. Yeah, well, you know, what's wrong with the 1/6 is it should be a 1/12. So my 1/6 here confused me here. That should be 1/12. So this should be a 12 here. Okay, now that's going to work. And then we're going to have on this term, going to be kind of sloppy, but we're going to have 5 times this. And that's going to be within the orange. And then we're going to have 6 of them. So I haven't finished writing this term out, but that's going to work. Okay, so we're going to have then plus 6y, which is 6x squared. 6 times x squared over 6. That's going to give us x squared. And then 6 times -5/18 is going to be -5/3. So that's going to be -5/3 x. And right there, I remember writing a 5/3 x here. So that's going to go away. And edit better because we don't have an x term up here. So far, my solution is looking pretty good. Something's going to blow up. And then 6 times 7/36, which is going to be 7/6. And now I'm saying that 1/3, -25/18 and 7/6 darn well better add up to 0. I better add up to 2, but we'll work that out in a minute. And then we have the 6 times 1/12 e to the x, which is, and I'm just going to write it as 6/12, which is convenient because all my other e to the x's are in multiples of 1/12. Okay, have common denominator 1/12. Okay, so that should be about it. If I've got all the terms down, then of course, then all this stuff is this term. So if I've got everything down, that should be it. Well, if we add all this up, we get 0. Sorry, we get 0 e to the -2x, 0 e to the -3x. Yeah, I'll write those down. I don't know why I didn't want to. Okay, so there's my e to the 2x and e to the -2x, e to the -3x terms. My e to the x terms, we got 1/12, 5/12, and 6/12. Just to emphasize it, 1/12, there we have it. And we can see that this is going to add up to 1 and 5 and 6, 12/12, which is just going to give us our e to the x. And we already knew that was going to work out. And then from our solution to the part of the solution that gives us the x squared plus 2. We have on x squared, we just have one x squared term because the other, the derivatives and so forth are not going to give us x squared. So we get a plus x squared. That's easy. And I've said it, but I'm going to write out the coefficients. we go on x's, we got a 5/3 minus 5/3. And I'm out of board space, so I got to run over the line, but that's going to be okay. And then we have plus quantity 1/3 minus 25/18 plus 7/6. I think that's minus 25/18. Where are we? Yeah. Well, all this gives us exactly what we should. The only thing that doesn't give us 0 will be this, which is just an e to the x. And this, which is what it ought to be. And this, if it adds up to 0. Okay, well, does this add up to 0? No, sorry, it has to add up to 2. And it doesn't look like it adds up to 2. So something's probably wrong with my arithmetic. Let's just see how it works out. But 18ths, we're going to get 6 and 21, which is 27/18, and a negative 25/18, which means simply that I probably made a mistake in solving for C. My 7/36 is probably wrong because if it was right, I can fix that quickly maybe. Again, common denominator is 18. So we got 6 here. And added to 2, we're going to get -4, not what I got. But anyhow, we're going to get 6. Well, 6 minus 25 is -19, -19. And we still get 21. And is 18 times 6 really equal to 108? Yeah. And 21 over 108, yeah. Still get 7/36. Here, maybe I did something wrong in here, but I'm not going to belabor it anymore, except to take a quick look at those constant terms again. From y double prime, on the x squared, we get 1/3. On the x, we get 5 times -5/18 gives us a -25/18. And on the y, we have 6 times 7/6, and I think there's where it is. I didn't multiply this by 6. So that should be 7. That's not going to do us any good either, though. So I'm still stuck on this term, but if I manage to get this right, this should also be right. Take the 2a, we get 5b, we get 6c. Yeah, I don't see the error, but there's an error. Okay. Overall, except for this one little error that destroyed perfection, you see how this works out. Okay, the derivatives add up to what they add up to. Again, the solution to the homogeneous equation gives you 0 when you run it through here. And everything else here gives you what you should get, except we don't get that 2 because there's some error in my last constant. Okay. Now, that's great for this example. And 2 principles come out of this. If you have an exponential function here, just an e to some linear power of x, not an e to the x squared, for example, that would be, that just wouldn't work out because a lot of functions won't work out here. However, e to the x is a very common function, e to some constant, e to the kx. If it's e to the kx, you try ae to the kx, and you just do what we did over here. And it's going to come out in a very straightforward manner. The only difference between what we did here and what we do if we got some other coefficient, as I mentioned, is you're going to get powers of that coefficient in the second and first derivatives. If you have a polynomial over here, we just go ahead and use a general polynomial of the same degree. Okay, degree of x squared plus 2 is 2. So we use a general polynomial of second degree. And of course, that's what we did here, where we used ax squared plus bx plus c. Okay, well, there are other kinds of functions that are amenable to this treatment, specifically sine and cosine functions, and then functions that we build from those functions. And there's some general heuristic rules, but if you work out a couple of these things, you see how it works. So I'm going to do another one where we have a sine and a cosine. Okay, we have a sine or a cosine or some combination over here. So if I use the same equation, because there's no point in solving a different homogeneous equation, we can illustrate what happens with sines and cosines. So let's say we have the equation let's just say we have a cosine of 4x over here. What functions could we put in here that would give us cosines? Well, one thing we have to realize is if we just say, okay, let y be some multiple of the cosine of 4x, well then out of this, we're certainly going to get multiples of cosine of 4x. However, we're also going to get multiple of the sine of 4x, right? Okay, so I'll say we could try a cosine of 4x but some derivatives yield multiples of sine of 4x, which doesn't appear on the right-hand side. I'll just say it doesn't appear on the right. Well, what we have to do then is we'll add multiples of the sine of 4x. Now that'll give us some cosines of 4x. It'll give us more sines of 4x. And we'll be able to then say, okay, whatever the coefficients of the sines are for this function, they got to add up to 0. And the coefficients of the cosines have to add up to 1. We're going to have enough parameters and enough derivatives that that's going to work out. So now say YP, particular solution, good idea to use this notation, and you'll see it in the examples in your text. Okay, YP equals A cosine of 4x plus B sine of 4x. You know you got to have 4x in here because anything else is going to give you a cosine and or sine with that multiple of x, of that multiple of x, and that multiple of x doesn't appear up here. So, okay, well, fairly straightforward. YP prime is then negative 4a cosine of 4x, sine of 4x. Plus 4b times the cosine of 4x. And then YP double prime is negative 16a cosine of 4x and minus, not plus, 16b sine of 4x. Okay, so our equation, I really want to start up here, but limited board space, I want to try to keep on this board, so I'm going to write down here when I shouldn't. Okay, so equation, thus YP double prime okay, and just to keep track, that's our Y double prime. And then 5Y prime. Well, take all this and multiply by 5. We get minus 20a sine of 4x plus 20b cosine of 4x. And we'll circle that in a different color. And finally, 6y, and that's just going to be six cosine of 4x plus 6 sine of 4x. Now again, I don't think the watermark is going to mess things up, but and there we have it. And I'll circle this. And I don't like to use yellow and green because they end up looking very similar. But we have, okay, 6y here. And that should equal the cosine of 4x. So again, just in case, there we have it. Okay. Now, we just collect our terms, and we have a cosine of 4x here, we have one here, we have one here. And let's see, we have negative 16a plus 20b plus 6 careless a. Put a skinny a in there and put a skinny a in here. Okay, so again, negative 16a and a 6a gives us negative 10a plus 20b. So now we have, to get it right, negative 10a plus 20b cosine of 4x plus whatever we have times the sine of 4x. It's going to give us two coefficients. And, well, we'll see in a minute. Okay, so we have negative 16 and negative 20 is negative 36. And then 6 is 6. So we have negative 30a can't be. Okay. It's not negative 30a because those weren't all a's. So pretend I didn't do that, or go ahead and acknowledge it. But again, we have negative 16b here. We have an a times the sine here. So that's not going to be a like term with this one, but then this here, which ought to be a b. Now we have bs, and which probably appropriate. Okay, that's 6b sine of 4x. It's all garbled, but that's what it should be. So we have negative 16b and 6b, which is negative 10b. And it's going to be then minus 20a times the sine. And that has to equal the cosine of 4x. And right there is what we need to solve for a and b. Because the coefficient of the cosine of 4x has to be 1, we get negative 10a plus 20b equals 1. And the coefficient of the sine of 4x has to be 0. So we get negative 10b minus 20a. Well, let's line them up instead of just writing it down blindly. So we get negative 20a minus 10b equals 0. And that's a set of simultaneous equations that we can solve really easily. We could solve this one. Need an a there. We can solve this one for a, let's say, and we get, now let's solve it for b. We get b equals negative 2a. So we replace this by negative 2a. We get negative 12a equals 1. So a is negative 1/12. Okay, that's easy if I said that right, and if it's correct. But the way these line up, it's really kind of almost easier to multiply this second equation by 2 and add. If I multiply the second equation by 2, I get a negative 20b, so the b's go away. I get negative 50a equals 1. Now I said a was 1/12 in what I did before, so I don't think I said that right, but we'll see if it works out. Seems a little extreme. And let me just double check that because I really don't trust it. Okay, we have negative 20a. Multiply this by 2 and add it to this. Gives negative 48. Still gives negative 50a equals 1. So I'm going to pretend that's okay. And then if we plug a equals 1/50th, we get a 1/5 here. Actually easier to plug it into this one because we got the 0. But negative 150, 1/50th gives us a 2/5 here. So the 10b is negative 10b is 2/5. So 10b is 2/5. And I get b equals 2/50. And yeah, these numbers are kind of big, so I think that works out. Okay, so negative 1/50 times negative 10 is 1/5. And 20 times 2/5 is 4/5. 1/5 and 4/5 gives you 1. And this is twice as big as this, so that, and of opposite signs, so this is going to add up to 0. So I believe that's right. So we have yp equals writing it carefully, a cosine, where is it? Yeah, a cosine of 4x plus 2/50 sine of 4x. General solution. That's a bad solution there. A badly written word. C1 e to the negative 2x, C2 e to the negative 3x, minus 1/50th cosine of 4x plus 2/50th sine of 4x. Okay. Okay. So if your right-hand side is a polynomial, you try a polynomial of the same degree. If your right-hand side is a e to the kx, you try an ae to the kx. And I don't know why I wrote ka, except I'm thinking head, maybe. I don't know. Now, ae to the kx, that's just because I wrote an a here. Okay, if you got a cosine of omega x or a sine of omega x or omega t, because that's usually something that's time varying, you're going to use this. Okay. Those are your simple functions. Now, if you have like a x to the n e to the kx, if you think about it, your derivatives of x to the n e to the kx would have x to the n minus 1, x to the n minus 2, and so forth. So you would use something like x to the n e to the kx, and that would be like a, I'll say a1. And you use decreasing powers of x in front of this. And so forth. Okay, because if you take derivatives of this, you're going to get lower powers of x, as well as, this power of x. So you're going to need the lower powers to also appear in your trial solution, so that these coefficients can be, the coefficients that you don't want can be wiped out. Because you just use e to the n, e to the kx. If it's e, let's just say e squared e to the kx was your right-hand side, the derivatives of that for a second order equation would give you x squared e to the kx terms, as well as x e to the kx terms, as well as just e to the kx terms, which are not on the right-hand side, and you wouldn't have any way of manipulating your coefficients to get rid of those unneeded terms that you get if you just use this. And if you, similarly, if you have an x to the n cosine of omega x or an x to the n sine of omega x, you're going to use a1 x to the n cosine of omega x plus a2 x to the n minus 1 cosine of omega x plus some stuff, plus like a b1 x to the n sine of omega x. They don't really need an x to the n on that sine of omega x because you're never going to, yeah, actually you do, you're going to get one. So forget what I almost said. Plus b2 x to the n minus 1 sine of omega x. Plus, and so forth. And if you think about it, it's just common sense that you're going to need these things. As we did in the example we did right here, where we needed a sine as well as a cosine. If you had an x cosine, then you would need x cosines and cosines, because you're going to get just plain old cosines too when you take derivatives, and x sines and just plain sines. So it's really pretty close to common sense. Now, there are a lot of things that you can't use. If you have a 1 over x over here on the right-hand side, it's hopeless. Not hopeless to solve it. We can use variation of parameters, which comes along after spring break. We do have methods, but the problem with like 1 over x is there's no end to it. Like you get a 1 over x squared term and a 1 over x cubed term and so forth. And they aren't going to match up. Okay. Arctangents, tangents, most functions that you can think of to write down aren't going to work, but functions of this nature do work. And since those functions are very common in applications, this is a good method because it's a little simpler than the variation of parameters method. Okay, well, that'll be it. Now, quickly, what I've done with your schedule is there is an assignment that'll be due the Monday after spring break, but I've cleared out the rest of that week for a midterm exam. What we could do is we could go ahead and have a midterm exam that week, which is closer to the midterm, or we could wait another week and include all of chapter 4. So give it some thought. Do you want to have a midterm, say toward the end of the week when we come back from spring break, that cuts off at section 4.5? Or do you want to go ahead and finish up chapter 4, include the variation of parameters in the review section, and do it a week later? And you might think how that fits with your work schedule and other courses you might be taking and other things that are going on in your life. Does that make sense? Are you still with me?
Yeah, that does.
Okay, we'll give that some thought and we'll talk about it Thursday. It makes no difference to me. Either way, I'm going to have all the spring break to construct a truly evil midterm exam for you, because it's the only way I can show my respect. So I'm not going to make it too evil. If we were doing this in class, it'd be a little more evil, but it'll be a good midterm regardless.
Okay.
It'll be pretty straightforward if you know how to do everything. I'm not going to, pull out the stops and do anything terribly tricky unless the temptation just gets too much, in which case it probably won't count that heavily. So, okay, so that's our plan. And I know you need to get back to work, so if no questions, you're welcome to move on. If you got questions, I'll be glad to answer.
All right. I'll see you Thursday.
Okay, good deal, Richard. Take care.
You too.